Right, I'm going to talk about Big Bang today. We embedded the story of physics in the human story. We had a bit of a look at that on Monday. And now we're going to get into more of the meat of the physics and then ending with the Big Bang, or as Calvin calls it, the horrendous space kablooie. There's some stuff on Galileo on the classroom, collected snippets that you don't often hear in the story of Galileo, which I find is quite interesting. We finished with him on Monday, and the birth of telescopes and increased accuracy in data, Tycho Brahe's data particularly, helping Kepler, and then Galileo improving on the telescope, making really accurate observations, started to put our understanding of the solar system in a different framework. Galileo was kind of 1630s. A number of years later, Cassini comes along and does planetary parallax measurements, starts to get a bit of a picture of the scale of the solar system. The first parallax measurements had actually been done 182 BC by Hipparchus. He measured the distance to the moon, two simultaneous observations in different places of the eclipse. And you could get the angles against the background. You could calculate the distance to the moon if you assume the star background was really far away. Cassini did that with better equipment, obviously, with a telescope, and with his colleague, John Ritchie. So from Paris and French Guiana, they measured the distance to Mars at the simultaneous time and got a distance. So we're starting to expand our understanding out along a distance scale into the universe. Cassini also did some very accurate measurements on eclipses of Jupiter's moons. This is the Sun, this is the Earth's orbit. This is one of the moon's orbits around Jupiter. As you watched one of the moons, the time it took for the start of that to the end of that is a fixed period of time. And during that time, the Earth would have moved from, say, point F to point G. Okay, the distance the light had to go from the start of the event was different from the distance the light traveled at the end of the event, because the Earth's moved closer to Jupiter. So the light had to travel less distance to signal, okay, the moon has fully moved into the shadow. Okay. And then if you're coming away from Jupiter and around the other side, the start of the event, the information would take less time to get to you than the end of the event because you're moving further away. And using those two measurements, he was able to compute the difference that in the time taken related to the speed of the light over this distance that you were in a different position for the start and the end. So not only was there a start of a scale of distance, but that was also mapped onto the start of a scale of time, sense of time. Information was taking time to get to us. So as we looked further and further out into space, we were actually looking back in time.
What's kind of like between point F and point G? What's kind of difference in time?
Different in time? I'm not sure. So it's the time for one of the moons to pass into the shadow. I mean, the distances here are exaggerated. They knew the distances of the orbit of the Earth. You could calculate this distance. You knew the difference in time it passing into the shadow, and you could work it out. So all this kind of information was effectively hidden before telescopes and before that iterative building of accuracy.
Really sorry.
No worries. Just looking at the first rungs of the ladder of the cosmic distance scale, started with Cassini, measuring first distances to Mars using parallax, and then also working out the speed of light using eclipses of one of Jupiter's moons. Okay, so we now have other ways that you can measure distances directly. So we can do radar ranging to get a direct timing measurement, say of Venus. You send a radar pulse, you wait for the echo. Now that we know the speed of light, you can get the distance using time. Parallax has extended. So you had Hipparchus in 182 BC doing it with the moon, then Cassini, and then Bessel did it with, I think his was 1838, the first stellar parallax. And now with the satellite Hipparchus, we've got our maximum baseline that we can do stellar parallax even further. And that distant measurement overlaps measurements that we based on the theories of star evolution and Hubble's distance scale of Cepheid variables. Okay, so first of all, main sequence, the star chemistry and the physics of stars. From observations of light, you could tell that different materials emitted different spectrums. It wasn't understand why initially. That had to wait for the development of quantum mechanics. But the different colors are discrete fingerprints of what chemicals are doing the emitting. And stellar atmospheres are made up of two things. One's the black body radiation, just the temperature of it. You also get the chemistry of the atmosphere layered on top of that. So this is the example of the sun. This curve is the black body curve. If you're in the quantum course, we talked a bit about that. So that's related to the temperature of the stars. If you know that, you know the temperature of the stars, and then you know the distance of the star, you can measure the total amount of energy that you're receiving. You know the distance, you know the temperature. You can measure the total amount of energy then coming out of that star. Therefore, you can work back and work out the surface area. And from that, you can build up a model of stellar physics. So you get some laws of stellar physics. And then if you have a star that's further away, that you don't have parallax measurements to, but you can see that it's the same as one that you know, you can then use that to extend the distance scale just a bit further. Okay, so that's the change in the spectrum with temperature. So you use that plus these absorption lines. I'll come back to that. Okay, so we've got the stellar chemistry. The next bit is the Cepheid variables. There's some types of star in our galaxy where we can see that their period relates directly to the overall output of light. So we've got a link between something we can observe directly, the variability of the star, and the distance scale. So Hubble, once he had the data, he could look at Cepheid variables in what looked like nebula, clouds of gas. And there was an argument about whether these nebulas were objects in our galaxy or were actually much further away. But because the Cepheid variables were so faint, he knew how much energy was coming out of these stars because they knew what they were. But because they were so faint, they must be way further away than in our galaxy of the measured stars. So it suddenly took our universe from a scale of what we now call the Milky Way, which was thought to be the universe. We now have other islands of stars that extend out. And in doing that, the light could be seen to be changed. All these stars that were further away, you could look at the fingerprint and see that it was shifted. You're all aware of the Doppler effect. So if a siren is coming towards you, it sounds high-pitched, higher frequency. It's going away, it sounds lower frequency. In terms of light, that's either a blue shift, if it's coming towards you. The light gets squished together, so the visible color spectrum goes towards the blue end of the spectrum. And redshift, if it's going away, you're stretching out the light and you see the pattern shifted to the red. Yeah, Elliot.
And the absorption lines, how do they tell? Is it just like something they inherently knew about the chemistry?
So each element has a pattern of lines, okay, that's to do with the levels in a specific element. So you could see hydrogen's lines don't map up to, so if you've got cold hydrogen around a star, it absorbs those lines. If you have some carbon in that atmosphere, it'll absorb a different set of lines. Those lines will be in the same places all the time. And you'll be able to identify, oh, there's that percentage of carbon there, there's that percentage of hydrogen, etc. But then once it's redshift, that whole fingerprint gets shifted towards the red end of the spectrum.
I see, but the actual absorption lines for different elements are like further enough away that they would get confused with. Yeah,
there would be a mathematical relationship that you could see because there's many different lines. They're each unique for each element. Okay, so you don't get confused. It doesn't, like if you shift one, it doesn't suddenly look like another element, and you can work out that redshift. Okay, so now we have distance data and redshift data, and if you plot those against each other, you get another distance scale because this is Hubble's law. He discovered that the further things are away from us in terms of that cosmic ladder scale, they're also moving away from us more. Okay, and you wouldn't expect this in a static universe if everything's just moving at random. Some will be moving towards us, some will be moving further away from us, and you get local variations in movement. But as you get further and further away on your cosmic distance scale, the overall Hubble movement of things moving away from us faster and faster just overrides that local random movement. Okay, so you get predominantly redshift as you get further away, and obviously further into the past. So we're seeing further into the past, and this light is being stretched out. Okay, so we've got now our foundations of the Big Bang theory. So we've got, well, at this stage, Einstein, his theory had been established before Hubble came along and had predicted the universe must be dynamic, okay? He had fudged it because at this stage, well, most people believed the universe was eternal, mainly from a philosophical idea linked to the Greeks, similar to their idea that everything must move in circles, it must be perfect, everything's, the universe is eternal. And that was the starting position. It was so ingrained, that worldview, that Einstein put a fudge factor in to, I mean, you've probably heard about that, the cosmological constant, to just make the universe static so that it wasn't evolved like general relativity, and also the cosmological principle that when we look everywhere, it looks the same. That's Hubble, redshift. So we're now at this end of the distance scale, Hubble's law with the redshift, and there are other possible measurements that extend out that distance scale. There's more detail on the cosmic distance ladder on one of the links in the classroom. Okay, next bit of evidence. Ober's paradox was quite an old philosophical problem. So if you had an eternal universe and it was full of stars, every line of sight possible would eventually end on a star. And effectively, the sky would be as bright as the sun, the surface of a star, because there wouldn't be any gaps. If there was a place you passed through the stars, then you just go further, wait for a bit longer, and the light from another star would hit you. Elliot, first then.
But couldn't it be that some of the stars are so far away that there's like so much like energy loss that we don't?
Okay, so that's a good point. So you could have absorption of material in between. Okay, and that's one of the proposed solutions. So the trouble with that is that if you absorb radiation, you're going to start to warm up. Okay, and if you've got an infinite time to warm up, you're going to hit equilibrium, and you're going to be at equilibrium with the radiation hitting you, so you're going to start to shine as bright as any radiation hitting you. Very well spotted, but yeah, that's exactly right. So that was potential, the energy was lost, but then because we know things will heat up, if you've got an infinite time, then that should heat up to the same temperature. You also had a question?
I was going to ask the same question.
Cool. Okay, so if the universe is infinite and static, it should be as bright as the sun. Brightness of stars decrease with distance, like we talked about. Just the inverse square law. But the further out you go, the more stars you encounter, and that balances out exactly, okay, in a flat universe, obviously. So the number of the stars in a spherical shield around us, it increases by the same amount as their brightness decreases. So therefore, each shell of stars is going to have the same overall luminosity, and like we just said, any intervening material would be absorbing that starlight, and it would heat up and start radiating. Okay, now, so the solution to this is also suggested by Hubble's observations of the redshift. Okay, so what do you know about the energy of a photon when it gets redshifted? Yeah, what? So a blue photon compared to a red photon, what's the difference in energy? Yeah, so there is a loss of energy with redshift. So the fact that it is moving and the universe is expanding has stretched that light out. And if you incorporate that, then each shell of stars further and further away gets dimmer and dimmer and dimmer. Less energy in each shell. Okay. So no matter how, let's stating Ober's paradox. But the solution is light waves are stretched out, so energy is reduced. But also one other thing, you need a finite time. If you still had an infinite time, then you're back to the same problem. But if there was a finite time for that light to travel to get to you, there's an ultimate cutoff point as well. Okay, so we're starting to build up more evidence for the Big Bang, or the horrendous space Kablooie. So all this stacks against the universe being eternal. So we have the Hubble law, the distance versus the redshift. We've got very good evidence that that's true. Obler's paradox is completely solved by the Big Bang model. We've got the homogeneity and isotropity of the universe. Very good evidence that our location in the universe is not particularly special. Looks the same in all directions. So that's the Hubble deep field. Same in all directions, but if you compare objects close to us with further away than us, you can see that they're different. Okay, so it's homogeneous and isotropic, but there's evolution. Okay, so another piece of evidence against the universe being eternal. These older objects look different. So particularly things like quasars in the very high redshift, very early universe look very different from galaxies that have evolved to be more recent. There's a very clear progression of structure change through the universe. Okay, so we've got evolved structures, and then last bit of major evidence was the cosmic microwave background. The conclusion from this picture, this model, if we wind back the time scales, everything's moving further away. In the future, it'll be further away from us than it is now. In the past, it will have been closer together. If you wind back the clock and just use Hubble's relationship between the speed and the distance, you can get a time for when everything was on top of each other. And you can work out it had a temperature. The whole universe effectively was at some stage like one star, and everything was expanded out of that. If we're looking back through shells of time, at some point we're going to hit that point when the universe is opaque. There's not stars with space, but there's just one universal star. Okay, this protostar. That was also, it was suggested by Belgian priest Lemaitre, and so this was his primeval atom. But from the chemistry that we knew, from the physics that we knew, you could work out what the temperature of that was and how it evolved. There was a prediction for, okay, we should see that radiation, and there was a prediction of what that temperature should be just from the expansion. So then we have the measurements of that radiation, which were first thought to be just noise caused by pigeon poo in a radio telescope, and they eliminated everything else. And when they realized that it fitted exactly this prediction from the Big Bang model that we should see this radiation, this was the final piece of the puzzle that proved the Big Bang. Okay, so this is a kind of illustration. So we're looking back in time through all these different layers of stars, and getting older and older and older to the point that we have this one cosmic star. It's a bit like, we can't see anything further through that. It's a bit like us hitting the clouds and being able to see that far back in time. Yeah.
I don't really understand how you work out like the timeline.
The timeline.
Yeah.
So the first point is the distance scale.
But how do you know what like the origin? Because obviously it's not like the center of the moon. So how do you know like what your your origin is to measure the distance.
Okay, so let's just when we're thinking about the Big Bang, it's not like there's one point that it originates from. Okay, so it doesn't have a center that then explodes out. So that's why I mentioned one of the key things was the homogeneity and isotropy. So everything's the same. So if you were on Alpha Centauri or a different galaxy, you would see the same thing, this cosmological principle. We're not at the center because there is no center. So if you imagine, if you're at A, it appears that everything's moving away from you. But if you're at B, likewise, it looks like everything is moving away from you. So the kind of visual model that's often used is of two dots on a balloon. So if you imagine a balloon being blown up, lots of dots on it, each dot will see the dots around it moving away, but there's no center which is on the surface of the balloon. The center is on a different dimension, and that gets resolved in terms of Einstein's framework of that center is in space-time as the beginning point of the Big Bang. Okay, so that's the kind of almost the center that we're kind of expanding out from. Yes.
So there wasn't really there's no kind of like background space-time that.
No. Yeah. Absolutely.
Was in.
Yeah. So I kind of think of it a bit like the number line. There's no the number references along the number line are just kind of points. You can stretch that out. What's it? The Hilbert's Hotel. Have you heard of that? Yeah. So space is a bit like Hilbert's Hotel. You can stretch it out, and there's still infinite places to put everything. Okay, so let's. We're going to run out of time. So there's also evidence of the evolution of the temperature of the cosmic microwave background. So you can. I'm not even sure on the physics of how you do this. It's very hard to get radiation measurements from different distances, but that plots against redshift as well. Okay, so we've got the evidence is the cosmic microwave background, only explained by the Big Bang theory. We've got different amounts of activity. It's greater in the past than now, so there's evolution over time. Number of quasars dropped off, so again, a evolution over time, and also the abundance of helium, hydrogen, helium, and lithium agrees with what you would predict from the stellar chemistry in this cosmic star. So basically, the Big Bang unifies all the observations we know into a coherent explanatory framework that now everyone accepts. And I will leave it there, and we will start having a look at some of the mysteries that this brings up, because it's not just about answering problems, it creates a whole other set of questions, and we'll look at that on next Monday morning. Okay. Very welcome.
Thank you, sir.
Welcome. See you on Monday.
Thanks, sir.